Those of you in Europe, good morning to those of you in the Americas, and I guess good evening to those of you a bit further east. Thank you very much for joining us today, taking some time out of your day. My name's Jim Webber. I am Neo4j's Chief Scientist, and the material I'm going to present today is kind of autobiographical. It's a bit about my journey discovering graphs and using graphs to build systems that have the appearance of some intelligence, and how that now meshes with contemporary trends in computer science and application development around machine learning. And it's going to be reasonably high level. There's not going to be any difficult mathematics or anything like that. I'm by far underqualified to teach the practice of ML. But I think reflecting on the experience that I and others in the community have had using graphs for ML, I think is very interesting, and I hope you folks will also find it interesting. And to reinforce what Sabina said, at the end, I'll try and answer as many questions as I can, so don't be shy. Please do type them into the question box. Any that I can't get round to during this session, I will take to email, so make sure your contact details are up to date, and I promise if I can't answer you verbally, I will definitely answer you electronically. It's only polite since you've taken the time to spend today with me. So with that, without any further ado, what we have today is this. So I'm going to introduce some very straightforward, no BS definitions around machine learning and artificial intelligence. I'll tell you a little bit about my history with Neo4j and the time I thought I'd accidentally invented Skynet. Since we all still exist and we haven't been overthrown by our robot overlords, you can guess that I didn't actually invent Skynet. But what it did lead me to was the field of graph theory. We'll cover some of the basics of graph theory, and then we'll have a look about how contemporary graph machine learning works. Following on from that, we'll take a somewhat speculative look towards the future of artificial intelligence with graphs, and cover what some of the thought leaders in the space are thinking with regards to graphs and AI. If that sounds good, stay on. If that sounds tedious, feel free to drop off, and I won't notice. So what have we got first? A bluffer's guide to what I call AI acronyms or acronyms. ML, very straightforward. We're going to find functions from historical data to guide future interactions, and this is specifically within a given domain. So it's a very prosaic, albeit very interesting field, but we're trying to use past data to guide future decisions. AI is the property of a system that it appears intelligent to users, and this today is often, but not always, done using ML techniques. Or a more broad definition of AI will be that it's a machine learning implementation that can be cheaply retrained to address neighboring domains. So you might train a model to recognize rodents in a building, and then you may be able to retrain that model very easily or cheaply to recognize bird life in a garden, that kind of thing. And that kind of transference thing is, I think, worthy of the term AI. I think you'll also hear the term AI, or particularly the phrase AI and ML, when people don't know what they're talking about. So be aware for that little gotcha. It's often conflated with things like predictive analytics, which of course have been around for a while. The whole idea of next best action has been around for a while before the more recent hype in AI, and conflated with general purpose AI, that is machine learning with transfer learning, so that learned experiences in one domain can be applied in other domains. This is human-like AI. When you learn that falling off a bicycle is painful, you choose not to learn by experience whether falling off a wall is similarly painful. You can infer those things. I think that's the kind of general purpose AI, which is, at least in regular IT, somewhat out of reach for the moment, but it's certainly something that's being pursued heavily in our domain. So what do we do today? Well, we ML all the things, right? We take our row-oriented data, our delightful tables, and of course, as a graph person, I have to object to tables. I think graphs are far richer. But we extract features from our tables. We extract sales history data or what have you. we train a model, and then from that, we use that model to predict good actions for the features. So we turn our rows into, we extract features from our rows, turn it into vectors, and pump it through a classification or a regression model. I think actually that's a really good thing. I'm quite genuinely amazed and tickled by some of the systems I see that are making use of what I think of as kind of classical ML in this thing. In this day and age. I think it's a good thing. But actually, we can do so much more before we even need to do this, and this kind of vectorization and so on, if we have graph data, because graphs themselves are very rich and can be, even naked graphs can be used to form the basis of systems that appear intelligent. So to set the scene, and of course I work for Neo4j, so I absolutely have to make this very clear. I stole this image from the Graph Algorithms book, the O'Reilly Graph Algorithms book. So you can grab a copy of that, by the way, from the Neo4j website for free, which is a very, very good price. It's an excellent book. And when I talk about graphs, of course, I'm talking about networks, the thing on the left. I'm thinking about how things connect to each other at, locally and at significant depth. I'm really not talking about histograms or bar charts or line charts or scatter plots or that kind of thing. Having now worked at Neo4j for 9 years, I've been chipped, and whenever I see those things now, I call them charts. Otherwise, my boss gets very grumpy with me. And so it turns out that, of course, graphs are very intuitive. You already know graphs. This is a very pertinent graph to where I live. In fact, it's what we call the tube map. And for those of you that don't live in London, the remarkable thing about this is that you already know how to get around London. For example, if I was to ask you, how do I get from a visitor's landing at Heathrow Terminal 3, and they need to get to the Neo4j office, which is at Southwark, which is Southwark for my American listeners. And actually, you'd already know the rules of that. You know that you'd follow the blue line, dot to dot, dot to dot, dot to dot, perhaps until you got to Green Park, and then you transfer onto the kind of grey silver line and go dot to dot, dot to dot, until you arrived at Southwark. And in fact, empirically, I can tell you that is the fastest way from Heathrow to the Neo4j office. But I'm guessing that very few of you decided to go from the blue line onto the green line, round the pink line, over to the east end of the city, scoot round the red line for a while before coming back, joining the brown line and going down to Waterloo and then changing and blah blah blah. None of you really wanted to do that. There was an intuition there that told you how to traverse this model, which is going from a node, a rounding, a station, via an edge or relationship to another node, and you chose the shortest path that you could find. And some of you might have found slightly longer paths than others, but intuitively you know how graphs work. And Neo4j, of course, embraces this. Neo4j supports the labeled property graph model. So we have nodes, which are, if you like, the entities in the graph. And in those nodes, you can put user data, properties, so key value pairs. And you can label those nodes with the role that it plays in the network as a customer or a product or a tube station in this case. And Neo4j, or the label property graph model, also supports named directed relationships. So that is, connects to or follows or purchased or those kind of things. So you can start to create little sentences, Jim purchased MacBook, that kind of thing. And relationships have exactly one start and end node, and they may also have properties on them. So in the tube example, you might choose to put travel times or distances on those relationships, so you can build a really high fidelity network. Now, this is it. The model is super simple. It's nowhere near as complicated as the relational model, which I guess many of us were taught at university. This is it. Ultimately, this is what you need to know to be sophisticated in graphs. And this is a mature model. This is, compared to Codd's model, the relational model, which is about 50 years old if you ignore the predicate logic precursor. This is a model which is nearly 300 years old. Right? Euler invented graph theory nearly 300 years ago, and now we can use these same idioms to build sophisticated data sets. Let me demonstrate it to you. I think graphs are the most natural way to model most domains. And you know this because when you're building software, you always draw sticks and lines on a whiteboard anyway to reason about system dependencies or communication flows in our software. I'd like to introduce you to a domain which some of you may be familiar, some of you less so. Doctor Who, my favorite TV show, the longest running science fiction show in the universe. That's right, suck it, Star Trek. The Brits got there first. And this is Matt Smith playing the Doctor a couple of regenerations ago. And let me tell you some key facts about Doctor Who. The Doctor is from a planet called Gallifrey. Although he looks human, he's actually a Gallifreyan or a Time Lord. And the reason he looks human, of course, is because the BBC has a very, very small wardrobe budget. And it turns out the Doctor stole this fantastic machine that enables him to travel in time and space called the TARDIS. And he has enemies. He goes around time and space battling bad guys. And in the course of doing that, he makes some enemies. And some of his most famous enemies are the Daleks, the Cybermen, and the Sontarans. And if you're wondering why I picked the niche Sontarans, well, I don't have my webcam on, but I visually resemble a Sontaran. So there you go. Now you know who's presenting this webinar to you. It's one of those kind of grumpy, baldy-looking guys. But the Doctor also is quite companionable. He often travels with companions here. In fact, this is Rory and Amy from a few seasons ago, and it turns out Rory and Amy have their own thing going on. They're in love, they get married, they have children, and all this kind of wonderful stuff. So there's kind of a social network element to this, which actually in a few minutes we'll look at from a graph theoretical point of view. And then all of this kind of fiction comes together in the real world. And you know, don't think I'm crazy. I obviously understand Doctor Who is fiction, but all of these different dimensions, the stories, the companions, the enemies, the space and time travel, come together in a physical deliverable, that the episodes that are broadcast or streamed to us as we consume the video. And those episodes have real world things attached to them, the screenwriters, the locations, typically in disused quarries in the English Midlands, and you know, the person that was the director, the person that was the caterer, and all that stuff. So you can bring many dimensions into a graph, which makes it really interesting because they store lots of interesting data. So if I was to ask you now, in which episodes does Amy battle the Daleks, I think even with a very limited exposure to graphs, you could answer this. You could see that the Doctor is the enemy of a Daleks, and that Amy is a companion of the Doctor. So kind of transitively, she's also an enemy of the Daleks. And you can see here that the Doctor, Daleks, and Amy all appeared in this episode, Victory of the Daleks. So knowing a few minutes ago, knowing nothing about Doctor Who, you now know a rich part, a rich seam of the storyline, and you know a bit about graphs. And of course, finally, what we add labels so that we know the roles of each of these nodes in the graph. And if you're wondering, yeah, we can. If you want to know who followed Matt Smith as the Doctor, we have had 2 regenerations of the Doctor since. And in fact, you could look through the history of the Doctor, so you could put effectively kind of time series data in this right back from the early days, and William Hartnell regenerated all the way through to Christopher Eccleston, and right now we have Jodie playing the Doctor. And if you want to query this in a graph, it's quite fearless. For example, if you wanted to know how I'm connected to the Doctor, I'm sure many of you have tuned into this webinar for exactly those reasons. The thing that a graph database like Neo4j gives you is the ability to explore connections very, very cheaply. So even for very large graphs, you could run either of these queries on the Doctor Who database, and you might find how I connect to the Doctor, either via a pattern match with a unbound depth, that's that little asterisk in the square brackets there, or simply by asking the database to run a graph algorithm for you to find the shortest path between me and the Doctor. And by the way, if you're wondering, I am connected to the Doctor, albeit at extreme depth. So that's me, an author. I wrote the book, the O'Reilly Book Graph Databases, with my friend Ian Robinson, who you see there beaming. Ian owned or was the main letter of a flat in Birmingham, England, which was sublet to an actor who subsequently played a character in a very hilarious series called The Thick of It, which we thought was political satire. However, we're now living through this thing called Brexit, and there is no political satire that could match real life nowadays. Nonetheless, in that series, The Thick of It, there was a very sweary character called Malcolm Tucker, And actually the same actor that played Malcolm Tucker ultimately played Doctor Who. So I'm connected to Doctor Who at depth 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm probably closer to Kevin Bacon, but I'm rather proud that I'm only 10 steps away from Doctor Who. So that's all of kind of basics of graph theory and graph databases. Now we can be smarter about things. We know that we have this data model at our disposal. This data model is very rich. We can encode a plethora of useful data in it. And so if we step back from simply trying to vectorize everything as rapidly as possible, what can we do? So think back in time, 2008, which frankly, given today's world, seems like halcyon days. This is the autumn of 2008. And I went to a place called Malmö in Sweden to give a talk at a really lovely conference called Uridev. And I was there to talk about distributed systems. And while I was there, I bumped into a chap and we got talking, and he told me about these things called graphs. And he said, what do you do? And I said, oh, I'm building distributed systems in telecoms. He said, oh, that's probably a graph problem. There's probably graphs in your database. And I said to this chap, look, I don't think you understand how databases work. Databases have tables, not graphs. And he then set about for the next few hours of beer and chat, convincing me about graphs. And that was nice, but then we departed, and I thought, wow, that was intense, and that guy's wronged. I went back to work and thought, hey, wait a minute, the problem I'm working on actually is a graph problem. I was thinking about how to provide recommendations within a telecoms environment. So for example, you would call in and the call center operative would say, oh, hi, Jim, how are you doing? Perhaps help me to solve a problem or something. And then based on what the purchase history I had with the organization, they might be able to recommend other goods and services that would suit me well. And it struck me in doing this that what I really had was a dependency graph. So given the things that I have bought and the things that they depend on and the things that depend on them, I could easily recommend things that I know the customer hasn't bought and that are likely to be good purchases for the customer, assuming the product creation strategy was good, which I think it was. I started to think, well, what was that thing again that that guy in Malmö, Sweden, was telling me about? Graph database. Yeah, that was the thing. And what was it called again? It had a really bad name. NeoDB, NeoMatrixabase, something, Neo4j. That's the one. So it turns out I'd been speaking to a chap called Emil Ephraim, who's now my boss, and this is being recorded. So this is probably like like a kind of the world's longest suicide note. But I picked up Neo4j, and it was frankly a Maven and Java hellscape. It was truly awful. This is a 0 point something version of Neo4j. And it was kind of like, figure it all out for yourself. The docs were bad and so on and so on. But in one long day, I managed to import some reasonable data into the database and ask it a question. And the question I asked it was, you can see there, encoded in Java, that kind of low-level traversal API stuff. I asked it, I said, given that I have home broadband and home phone, what should I buy next? And it told me that I should buy platinum broadband, so a better quality of broadband, and voicemail. And for a brief moment, I thought, oh my God, this is Skynet. And of course it wasn't Skynet. It was just graph traversals. I was doing a search through a graph, through a dependency graph, and the searching thing, the database in which I'd stored this graph, was able to tell me, based on what I had, other things that depended on it. And it told me that very quickly, and I was absolutely amazed. Then I was hooked. This tech hooked me, because not only was it humane to model with, I built this in an afternoon, a long afternoon, but I'd never touched the tech before. And then suddenly I was able to answer questions that we thought the off-the-shelf system we were going to buy might answer in 3 years. So this was kind of years to hours kind of collapse of complexity, which was amazing. Just fantastic. Never sold the customers anything incompatible, never tried to sell them something they already owned. And of course, we know even today, those things happen all the time. Go to Amazon, buy a pair of shoes, all they sell to you for the next 12 months is more shoes. And of course, I'm a biped, so I have a statistically slightly higher number of legs than the average human, but I'm certainly not an octopus. I don't need 8 pairs of shoes. So this was like incredibly and unexpectedly powerful. Solved a problem in an afternoon that was meant to take years with off-the-shelf software. The effect of this is that I kind of swallowed a bit of humble pie and talked with my boss Emil again, and I joined Neo4j in 2010. And from there on, I had some amazing experiences building both the database and seeing Neo4j users build very intelligent seeming systems. So over time, Neo, as many of you hopefully know, matured into what I think of as a proper database. It has Cypher as a humane query language, and it's a kind of normal server-based graph database, as opposed to a Maven plugin library, Eclipse super-powered pain in the backside. I think it's amazing and it's humane to implement. So when I joined Neo4j, the next thing I worked on was for a retailer in the UK, a proof of concept for a retailer in the UK, a large supermarket. And it was, again, recommendations based on what people have bought, recommend them or their similar demographic what they should buy next. And at the time, we were tickled by this urban myth that on Friday nights, a large retailer in the US had stated that if they place beer on the end cap of an aisle which sells nappies, diapers, that they would sell more of both. And that urban legend tickled us. So we decided we would look at some parts of the data like this, where I have a customer that bought some products, and those products were in some part of a category. You can see here there are a couple of beers that are in the category of beer, which are in the kind of, ontologically, they're in the kind of category of alcoholic drinks. It's kind of a small ontology, but it suffices for this. And they bought some particular brand of nappies in the category of baby. And this Mickey Smith character also bought an Xbox 360, which is in the category of consoles, which is in the category of consumer electronics, and so on. So we have a data model. Some of it's taxonomical, like ontological, some of it's stock-centric, and some of it's transactional. All right, so we've got at least these three dimensions that we can bring into the mix. So we poured this stuff into Neo4j, and of course, you'll be unsurprised to hear that a graph emerges. And one of the things that we thought was interesting was this is what we thought of as a prototype, a pattern for young fathers. That is someone that's born between a certain age, and you can see my biases coming out here now that I've been a father for 7 years, and I keep changing that date of birth so I can still qualify as a young father. It's pathetic. But a young father has bought something in a game console, bought nappies, and bought beer. For those of you facing the prospect of parenthood, this is in your future. You won't be partying with your friends anymore. When the kid goes to bed, all you'll be able to do is glug a beer and take out your frustrations on the Xbox. So here we have some insight. This is what a typical young father looks like in our graph. Of course, if you were to machine learn this, you might get similar results, or indeed you might just, get something like this where your model classifies the person as a lazy, drunken gamer. That's fine. I'm afraid you can't ever unsee that. So surprise, enjoy your afternoon. But actually, there is a business opportunity here, and an interesting one. So if you've got a partial match on a young father, so for example, they bought nappies and beer, but they haven't bought a game console, then that's an opportunity to sell them a game console. And in fact, what you want to do is change their behavior in the clickstream or at the point of sale terminal. In the UK, when we did this proof of concept, the way that loyalty cards work, the kind of way that supermarkets gather data on you, was in batches. You would make your purchases at the supermarket, some batch processing would happen, and then some vouchers would be mailed to you. Physical paper vouchers would be mailed to you. And that's very latent, and the psychologists behind that knew that it wasn't a brilliant way of altering behavior. It was okay, but it wasn't brilliant. And it also, because of the latency, you could end up receiving vouchers for things that you'd already bought in the meantime. What they really wanted was to be able to make these decisions in real time, the kind of thing that, of course, graph tech can help with. So we took this graph and we turned it into text. That's the same graph, it's just written in text. And then we flattened it, and then we added some boilerplate, including any labels to map to labels in the database. And we added a match clause, and then we put our exclusion where the daddy, the customer, has not bought anything from the consumer electronics category, and we bound those nodes to particular nodes in the graph. We want the distinct daddies back, and we got an answer. So we could look through the whole graph to find individuals that we might be able to sell to. Hey, here's a voucher, 20% off Xbox. Or indeed, we could flip it around and say, for the current individual, what vouchers should we print for them at the point of sale terminal right now, including up to and including the things that have just been processed from the current basket. This was a major leap forward, and the psychologists knew that being able to place vouchers in a customer's hand is a profoundly more effective way of changing their purchasing behavior than sending them through the mail. This is a big win, right? Because this seems like my supermarket understands me better and is acting in my best interest by incentivizing me to buy things that it thinks I should want. It seems almost intelligent. Of course, from the supermarket's point of view, it's not all altruistic. I could have a glut of stock. I want to get rid of Xbox 360s because Xbox One's come along and so on. So these things work for both parties, and it seemed very intelligent. On the big wide web, of course, we've seen Facebook do something similar. Facebook's graph search is able to answer questions like, which sushi restaurants in New York City do my friends like? And this is based on a trivial knowledge graph here. So here I've got a small social network with me being friends of Andreas and Michael. And you can see that Michael likes iSushi and Andreas likes Sushi Zam, and they're both somehow connected to the cuisine sushi located in New York. Of course, this is quite a coarse graph. If we were doing this for production purposes, it wouldn't simply be location New York. You would have some more detailed geo-index there, an R tree or similar. But ultimately, Facebook's graph search feature works exactly like this. In Neo4j, you can map this very trivially. So database, match me a person who has the name Jim, who's a friend of another person who has a particular restaurant like in a particular place. In this case, the location is New York, that serves sushi, and tell me about it. But the marvelous thing about this, the absolutely truly marvelous thing, I think, is that even though this is a potentially large data set, citywide, countrywide, worldwide even, the latency of the query to find this information is bounded by how much of the graph you choose to search. It's not proportional to the overall size of the data. So you can have huge graphs, and if you craft your queries well and bind them locally, you can still have very, very efficient, low latency, millisecond level queries, even for huge data sets, which is great. So given all of that mechanics, how can we start to make intelligent responses from our data? And I think the way to do this is through, initially at least, through the field of graph theory. Now, if any of you on the webinar are data scientists, I have a job tip for you. Read these two books. These two books are astounding. Rebrand yourself as a network scientist and demand 20 grand more from your employer. The Easley and Kleinberg book, Networks, Crowds and Markets, is it's probably about a decade old now. It's absolutely brilliant. It's a real page turner. Both of these books are academically oriented, but both tremendously readable. The Easley and Kleinberg one mixes graph theory and game theory, so extracting intelligence from connected data. And the Bianconi book is a bit more mathematical, but it's about how to effectively have layered networks such that you can slide layers in or out of your model to add more or less sophistication, color, and context for the kind of queries you want to do. I cannot, apart from the two O'Reilly books that the Neo4j team have written, I think these books are just super amazing. And what we get from graph theory is this rich 300-year-old knowledge of how graphs operate in many domains. And of course, particularly in the human domain nowadays, we have that from the online social networks. We also have a bunch of off-the-shelf algorithms which enable us to process those graphs for information, insight, predictions, and so on. And actually, the barrier to entry is pretty low. A lot of the tools are already out there, encoded in libraries, encoded, for example, in Neo4j, and they're amazingly powerful. Let me tell you about some of the things. So first thing we're going to talk about is local properties. And the most fundamental local property in graph theory is this notion of a triadic closure, which is kind of a kind of Hogwartian phrase, to be honest. It's I think it's designed to intimidate. In normal human English, this just means make triangles. And in many social graphs, graphs involving people, there is this tendency to make triangles. So here you see three humans, Kyle, Stan, and Kenny. And you can see that Kyle is friends with Stan and Kyle is friends with Kenny. And you've probably felt this in your own social networks, where you have two friends whose company you enjoy and you think they're lovely people. The chances are at some point they're going to meet and they're going to hit it off and they're also going to become friends, right? So this kind of triangle appears where Kyle is friends with Stan and Stan and Kenny themselves become friends. And that's nice. I mean, of course, some of us on this call are computer scientists and we only have two friends, and that's too bad. But I think we can always imagine how the normal people with their vast and extensive and wonderful social networks, these kind of triangles form happily for them. There's also this notion in triadic closures of structural balance. So actually here we have these other humans. They're taken from the South Park universe, in fact, and we have Cartman, who's rather a nasty fellow, and Craig and Tweak, who are two other kids at Cartman's school. And Cartman and Craig are friends, but Cartman is the enemy of this other kid, Tweak, and yes, aren't kids terrible? And so one triangle that could emerge from this is that Cartman and Craig remain friends, Cartman and Tweak remain enemies, but somehow Craig and Tweak become friends. And this is an unbalanced closure. It's kind of an awkward triangle, right? Because you can imagine, kind of Craig and Tweak, or Cartman and Craig having a chat, and Cartman might say to Craig, "Hey, look, I really hate Tweak. Let's do something terrible to him." And Craig's response would be, "Well, no, actually, I like Tweak. He's my friend." So that's quite an awkward triadic closure. It's what we call an unbalanced closure in graph theory. And what's actually a balanced closure is actually this, where Cartman and Craig are friends, but they're both enemies of Tweak. Now, there's no moral story here. This is awful and kids are awful and all that. But here you see the triangle makes sense because Cartman and Craig can now collude against Tweak and do nefarious things to him, which is terribly sad. Oh, terribly sad. So we have this kind of idea then that we have structural balance where we can have one friend relationship and two enemies, but equally we have a structurally balanced closure back to our friend relationships between Kyle, Stan, and Kenny, which is much nicer, right? And I do enjoy showing minion cartoons to you sophisticated software professionals. I do enjoy that. So this local property, this structural balance property, is a key predictive technique. Given a history, it can predict the future, and it's domain agnostic, and it's eerily accurate. So, for example, here is a historical rendering of Europe. It's actually an arrangement of the great houses of Europe about 100 and odd years ago. It's called the Three Emperors League. And in this graph, the red arrows show enemies and the black arrows show friends. And you can see clearly in this graph that there are already some structurally balanced closures, right? So Austria, Germany, Russia, the Three Emperors League, that's friend, friend, friend. They like each other. And you can also see some more negative balanced closures. Austria and Germany can gang up on France. But the rest of this graph is relatively unstable. The UK, France, and Russia all are enemies. So somehow there's some pressure there for one of them to become friends with the other so they can gang up on the third. You can feel that social pressure right there. Then what happens is that Italy, who was disconnected, joins the fray. And they form a subgraph, which historians call the Triple Alliance. They become friends with Austria and Germany. They create a stable triadic closure there. Then the Germans and the Russians lapse, and we get this thing now where Russia has increased enemies. We also, we also then see that France and Russia become friends to form a stable triadic closure. So it's almost like the graph is always trying to get to this low energy stable state. And this is an interesting one, right? Because it now means that France and Russia are friends, and one of their common enemies is the United Kingdom. They have another common enemy in Austria, so they could gang up on, and indeed another common enemy in Germany, so they could gang up on any of those folks. Then something tremendously weird, given the previous millennia of history, happens, is that France and the UK enter into the Entente Cordiale. And this is super weird, both because of history, but also because now Russia and the UK hate each other, but France likes both of them. So there's a tendency within the graph for that to repair. And in fact, the UK, the British and the Russians enter into a format called the British-Russian Alliance. And as you iterate over the rest of this graph, simply making structurally balanced triadic closures, you end up in this low energy state for the graph, where everyone is part of a structurally balanced closure. And in fact, iterating over that graph, we find that we end up here, which amazingly, that graph theory has predicted is actually the starting point for World War I. So yay for graph theory, boo for humanity. And in fact, this is written up in the Easley and Kleinberg book, where they show that even without knowledge of great houses and egos and wars and so on, that you're able to use graph theory by making these closures to be able to take your graph, iterate over it to predict how it will mutate in the future, which is super surprising, right? It's a really surprising, super surprising property that graphs can do that. Another interesting property of graphs, the strong triadic closure property, is that if a node has strong relationships with its two neighbors, then these neighbors must have at least a weak relationship between them, because it's going to form a closure. So in this case, for example, we might have Kenny, who's friends with Stan and Cartman, but Stan and Cartman are kind of like meh friends. They're acquaintances. They're not enemies, but they're not super strong friends. These weak relationships are really important, and because they often provide the links or bridges between subgraphs. They bridge neighborhoods in a graph. To return to the playground analogy, you can see here that this is again South Park. The boys and the girls are quite disconnected. Stan and Wendy are the only kind of boy-girl linkage there. So any information that flows between the boys and the girls has to go through Stan and Wendy. This is the same kind of thing that you'll see happen in your organizational charts. There'll be weak links or bridges between neighborhoods through which information flows, which doesn't necessarily reflect the tree of your organization. And so we have this idea of a local bridge property. So if a node in a network satisfies a strong triadic closure property and it's involved in two strong relationships, then any local bridge it's involved with that bridges two subgraphs must be a weak relationship. And we can use those weak relationships to evolve the graph as well. So here is an example known as Zachary's Karate Club. It's from the 1978 United States Journal of Anthropological Research. And yes, if you're wondering, the cold winter nights do fly by in my house. And you wonderful humans, you can look at this graph and you can already see clumps. You can see kind of a clump around node 1 and a clump around node 34. And actually, we can partition this graph by picking apart the weak links iteratively, such that we can partition the graph. And in fact, in Zachary's Karate Club, this is exactly what happened, right? So what happened was the node labeled 1 was the original founder of the Karate Club. He was a student at the university. And as the club had grown, the club also decided it should hire a professional instructor, and represented here by node 34. And what happened was that ultimately the club parted, two cliques formed, and there was evidently some animosity. And the question was, can you predict how the club would split? Because we know it did split from history using graph theory. And in fact, this is what graph theory predicted. By picking apart the weak links, effectively identifying the clumps in the graph, graph theory predicts that all of the white nodes would split off in a new club with the professional karate instructor, and all of the pink-colored nodes would stay in the old club with the former student karate instructor. And what's interesting here is graph theory got it wrong. Watch node number 9. This is what actually happened. Graph theory was so close. So it could, by picking apart all of these weak links, create a future graph or graphs and predict the schism in this club. What it couldn't know was that node number 9, or the student represented by node number 9, was close to completing their karate exams, a first dan examination underneath the original student instructor. So although they were much more tightly socially bound into the white graph, they ended up staying in the pink graph for pragmatic reasons. So this is great. So we have these like super cool properties which can predict the future given the past. If you're going to run this stuff on Neo4j, great, please go ahead, download Neo4j. Neo4j comes with both the database features and a bunch of graph algorithms to help you do this kind of centrality finding, clustering, subgraph analysis, triangle counts, all this stuff for free. You call it easily from your Cypher query, just call the algorithm and off you go. And it's incredibly performant, incredibly so. You don't need huge macho clusters to add to the planet's carbon footprint to do this. In fact, my friend Michael Hunger, a colleague at Neo4j, was asked to page rank a payment history for a large internet payment provider. And it was like 300 million nodes, 18 billion relationships graph, page ranked in 20 iterations, and it took 2 hours on a modest computer now, 12 hyperthreads, 128 gigs of RAM, in less than 2 hours, which was a job that that payment provider thought might take hours or days on a large Hadoop cluster to do the same thing. So you get amazing performance on Neo precisely because it's optimized for graphs. But of course, the finale of this is about contemporary AI. Now, hopefully there are enough of you on this call that remember this, but when I was young, we were all absolutely convinced that AI would be in cars. So this is Kit, and he's an artificially intelligent vehicle. And the gentleman putting his thumb up is David Hasselhoff, much beloved David Hasselhoff of Knight Rider, Baywatch, and freeing East Germany from the tyranny of communism fame. And when I was a kid, AI was definitely going to be in talking cars. And I have to admit a slight disappointment that AI isn't really in talking cars nowadays, but in fact is in row and row and row of servers in machine rooms. I think the 80s had a better vision for AI, even if they didn't have a better implementation. So what are we doing in AI nowadays? Well, the graph structure is itself rich. Here's an example from KDD 2015. It's the Thacker et al. Paper. What Thacker et al. Were doing was understanding the structure of a graph to prevent spam messages flowing through a social network. They didn't look at the content of the graph. They just looked at the structure, the senders, the receivers, and so on. And what they found is, by understanding the structure of the graph, they could classify 70% of the spammers with around 90% accuracy by running algorithms, by extracting those features, by understanding the page rank or the centrality or the subgraph of any given message. They could identify 70% of the spammers with 90% accuracy without even looking at the text, without even analyzing the text to see if it contained Viagra or cheap loans and that kind of stuff. So graphs have this key advantage. They have structural context. If you're considering a node in a graph that represents a person, a user, or a message between users and so on, you've got this structural context in the graph which isn't available in other data types. And this gives you this incredible advantage that you just have context. Now today, we take GraphML is still about turning graphs to vectors using Graph2Vec and friends. But these are highly complementary techniques. I think mixing structural data, extracting connected features gives better results. If you are injecting vectors into your ML pipeline, which contain connected features, the results of PageRank, the results of label propagation, or so on, you're simply putting better data into your models, and then you'll get better results out. But of course, we don't always have to vectorize graphs. We have a range of other options. Ones that particularly seems popular nowadays, and I think about eBay. I talked a few days ago to a large cloud provider who want to do this for their users. It's the notion of a knowledge graph. So semantic domain knowledge for inference and understanding. And the eBay Google Assistant, I think, is a really good example of this. So I talk to my Google Home Assistant, or at least I can if I'm in the US, and I can ask it to help me shop on eBay, and I will get a shopping experience that's tailored to me. And so when I talk to my Google Home Assistant and say, hey, I need a new bag, it knows what I mean. It looks at my purchase history, it understands my demographic, understands that I'm a middle-aged bloke, looks at my purchase history and finds that I've got a thing for laptop bags. So when I say something as vague as I want a bag, it can help guide me to that part of eBay's enormous and dynamic catalog, and then guide me through, given my demographic, my history, and so on, guide me through to make what are probably good recommendations. Similarly, if my mother-in-law was to use the system and she said, I need a new bag, for her, it would actually be a kind of utility bag, handbag kind of thing, and the system would understand that context, and she would be guided through the graph. This seems, when I see the system, it seems incredibly intelligent to me. This richly connected data over multiple dimensions makes the system seem intelligent. But in reality, this is just data and algorithms. This is just a graph and traversing that graph which gives us the kind of impression of a intelligent system. But if we are really going to do graphs for real and do graph ML for real, I think the paper from Kipf and Welling at ICLR 2017 is interesting. I picked this up, full credit to Andrew Doherty at CSIRO in Sydney, Australia, for pointing this out. And graph convolutional neural nets are a general architecture for predicting node and relationship attributes in graphs. And so the idea is here that you would kind of have a graph of movies that a user liked, and you feed that into a neural net. And then you have a graph of users who rated one of those movies, and you feed that into a neural net. And then you recurse through that data until you get all the movies and all the users together. So you kind of end up with a load of embedding vectors, fancy hashes that place like near like in some high order vector space. And then you end up with a group of back-propagated trained neural nets. And this method is really, really interesting, right? Because not only is it better than collaborative filtering, it deals not just with bipartite user likes movie kind of graphs, but kind of k-partite graphs. So user likes actor in movies with genre screened in London at a cinema where they serve cheesy popcorn kind of thing. So you can have much richer graphs in this, like a k-partite or multipartite graph. And in fact, this system is scalable both for training and for prediction. And this isn't some, although Andrew Doherty is a researcher in this stuff, this isn't some like fancy pants academic stuff that we're not going to see in practice for years. This same architecture is the thing that underpins YouTube's recommendation engine. So if you're wondering, how so many people get radicalized with crazy ass YouTube videos, it's this setup that's feeding those people and feeding their addiction and getting them recommendations that, for some level of right, are right. They do the same thing for my kid when he's on YouTube. It's feeding him kind of video game stuff and other young kid stuff that they think he will enjoy. And it's using this same graph-oriented architecture, the graph convolutional neural net, to get there. So I think this is practical today. The YouTube folks, the Google folks have published stuff on this. I think this, to me, is kind of the premium level of graph AI today. But it's certainly not the premium level where graph AI will be tomorrow. Not too long ago, there was a position paper from really the kind of creme de la creme of AI researchers from Google, MIT, and Edinburgh University. And in this paper, they reason that, or this is a growing realization, that if you're going to have human-like AI, you must be able to draw analogies. You must be able to represent knowledge as hierarchies and then transfer learning between them. And the great and the good of AI are saying that this is a graph thing. This is a graph problem. So you're able to structure your knowledge in a graph and then provide cross-linkage between that knowledge, such that you can understand that if eating a cabbage tastes terrible, that you know that eating a sprout will also taste terrible. This is something that as biological beings, as humans, human infants already know this, but we're now starting to learn that representing data as graphs and representing learning as linkage between hierarchies in graphs is where where the research is going to be, at least in the near term. I think that's very, very exciting. So look, if all this stuff seems hard at first, we're used to tables, we're used to tabular databases, we're used to column-oriented databases and so on. And our toolkits, the popular toolkits, TensorFlow and friends, are very vector-oriented. It all seems a bit hard at first. But I guarantee that once you get over the initial learning curve of thinking about graphs and ML, or in fact, just thinking about graphs for intelligent systems, once you're over that initial hurdle, you'll love graphs. You'll be in the zone of graph love, and you'll never want to go back. You'll never want to go and do the other things because they seem hard and they seem poor of information. They seem information poor. So I'd encourage you, look, if you haven't used graphs to build intelligent systems in and of themselves, or you haven't fed extracted connected features from graphs and use that to improve what you're feeding into your ML pipeline, do give it a go. I think you'll get some very interesting results. And so, look, there's a vast gap at the moment, with respect to what we could do with graph ML today, deep walks, random walks, and so on, assign vector to node. There's very little, maybe 10, 20% of what we think of as true graph AI. So it's a whole range of things that you folks could do in terms of graph, machine learning, and ultimately artificial intelligence. And I guess my closing note would be, With great power comes great responsibility. Do go ahead, build incredible graph-based systems, build intelligent systems, have fun doing it, but be responsible. So thanks everyone for listening. I'm Jim Webber, Neo4j's Chief Scientist.